Energy conservation in spring systems. Spring forces are conservative, and because of that, the total energy, mechanical energy, which is K plus U, is a constant. And since K is a half K x squared, which is parabolic, we have this energy graph. If we have some fixed amount of energy, then it's going to track out along that path. And the system's going to bounce back and forth between those two values. What values? Well, the values that are the amplitude. Of course, at the maximum, at the turning points, there's no kinetic energy, so it's just spring energy. Since we know the spring energy is a half K x squared, and at the turning point we're at the amplitude, the total energy, which must equal that maximum potential energy, is a half Ka square. Of course, the maximum kinetic energy would be also therefore be a half Ka square, but of course K is m omega squared, and so m omega squared is m omega squared a squared is going to be v max squared, a half m v max squared, because these are is v max. So we're getting a lot of relations that kind of trip into each other. But we find that we can also get the time dependence because we know that x is a cosine omega. We get that the potential energy has this form, 1 half Ka squared cosine squared omega t. Kinetic energy is a half mv squared, but v was minus a omega sine omega t, so we squared that out. We have 1 half m omega squared a squared sine squared omega t. So now we have the time dependency, which we've not usually done with energies, but we have available now. It's a special case. Something cute happens when we say, hey, let's find the total energy at any time, which would be K plus U, U plus K. We have 1 half K, Ka squared, whoops, I think I have a square there, K A square, cosine square omega t, plus 1 half m omega squared a square sine squared omega t. But remember that m omega squared is k. So this is actually 1 half k a square cosine square omega t plus 1 half k a square sine square omega t. We can factor out everybody who's not a trig function, and we get 1 half Ka squared, and then we have cosine squared omega t plus sine squared omega t. But way back from trig, we know that cosine squared plus sine squared for the same angle is always just 1. And so we end up that the total energy is, as said before, 1 half Ka squared, and it is conserved. As a function of time, these look like the things to the left, where we have the omega, the k term, which goes up and down as a sine squared. And we have the k, the u, which goes down, up and down as a cosine squared. And then we find that the sum is always just this horizontal line. All right, car attached to a spring is displaced from equilibrium release. There is no friction. Graph of velocity as a function of time is shown, of the velocity as a function of time. The arrows and signs indicate the positive and negative directions for the position of the cart. So, what is the period of this motion? In general, we'll want to go from some point to the equivalent point on the cycle. It is generally easiest to go from a max to the next max, or equivalently from a min to the next min, because then we don't get the double crossing, right? The maxes are unique in every cycle. We don't have to worry about the fact that it has that value twice. So we go from here and we say, well, that's from we end at 10 seconds, we start at 2 seconds, the period is 8 seconds. What's the frequency of motion of this cart? Well, remember that the frequency is always just 1 over the period, so it's 1/8, 1 over 8 seconds, or 1/8 of 1 over seconds, or 0.125 hertz. Keep in mind you can't read the frequency off the graph. In general, if you're asked for frequency from time data, you have to find a period and then invert. And then, in what direction is the cart displaced from equilibrium before it was released? Notice it's released from rest, so it is stretched to either its plus or minus amplitude, and then let go. Well, if it starts off moving rightward, it must have been displaced to the left. If it's going to start from rest, it's going to start here and move over.